Hey there. You know that big, powerful hum your air conditioner or your fridge makes right when it kicks on? We hear it all the time, but have you ever stopped to think about what's actually happening? Today, we're going to pull back the curtain on that sound and look at the hidden genius that gives these big motors the kick they need to get started.
Okay, so let's get right into it. That hum you hear is the sound of a motor fighting against inertia. That is, the physics of standing still. Firing up a big motor from a dead stop is a huge challenge. So we're going to break down that exact problem, and then we'll look at two absolutely brilliant solutions engineers came up with to solve it.
So here's the deal. To get spinning, the motor needs this temporary, super high power boost. It goes to a special part called the start winding. You can think of it like giving a really hard shove to get a heavy merry-go-round moving. But, and this is the important part, you can't keep shoving. If that start winding stays on for more than a second or two, it'll get crazy hot and completely burn itself out. The whole trick is to give it that push and then get out of the way at the perfect moment.
So, our first solution is this amazingly elegant piece of material science. The technical name is a PTC starter, but I like to call it the Smart Stone. And you want to know why it's so genius? It has absolutely no moving parts. None.
Okay, the name positive temperature coefficient sounds really complex, but the idea behind it is actually super simple. It's made from a special kind of semiconducting ceramic. When this little ceramic disc is cold, electricity just flows right through it, easy as can be. But when it gets hot, it's like it slams on the brakes and the electricity can barely get through at all. It's basically a smart resistor that uses its own temperature to work.
Here's how it all comes together. Step 1. When your AC kicks on, the PTC is cold. That means its resistance is practically zero, and a huge jolt of current flows right through it to that start winding. Boom! The motor gets the kick it needs. Step 2. That same rush of current immediately starts to heat up the ceramic stone, and this happens fast, we're talking less than a second. And finally, Step 3. As it gets hot, its resistance just skyrockets, basically creating a roadblock for the current. This takes the start winding offline automatically. How clever is that? It's a switch that works all by itself with not a single moving part.
And this leads to a fantastic analogy from our source material. Sometimes there's another component in the circuit called a capacitor, but at startup, the electricity just completely ignores it. Why? Well, because the path through the cold PTC is like a wide-open superhighway. The current takes the path of least resistance, bypassing, or as engineers say, shunting, the capacitor. It's just sitting there, totally out of a loop, like a bird on a wire watching all the traffic zoom by below it.
So what you end up with is just pure engineering elegance. PTC starters are incredibly reliable, they're super efficient, and they almost never fail. But the real win, the thing that makes engineers give this a major thumbs up, is that it solves this really complex timing problem with a solid piece of ceramic. Absolutely zero moving parts to wear out, to jam, or to break. It's brilliant.
But the Smart Stone isn't the only game in town. Engineers developed another solution, a bit more complex maybe, but just as clever. It's called the electromechanical potential relay. This one's less about materials and more of, well, an electric trick. Now, unlike that solid-state PTC, the potential relay is a physical switch. It's a little box with a coil of wire and actual metal contacts that move. And instead of reacting to heat, its trigger is something you can't even see, electrical voltage. Now, to really get how this works, you have to know one critical detail about its contacts. A lot of relays are normally open, meaning the switch is off until something happens to turn it on. But the potential relay, it's the exact opposite. It's normally closed. This is so important. It means the second you flip the switch, power is already flowing to both the main run winding and the start winding at the very same time. And right away, that brings up a really interesting question, doesn't it? If the start circuit is on by default, how in the world does it ever turn off? What's the signal that tells this physical switch to open up before the motor destroys itself? The answer is really cool. You see, the answer isn't really in the relay at all. The secret is actually hidden inside the motor itself, which is about to perform an incredible magic trick on itself. And the key to this trick is a concept called back EMF. That's short for electromotive force. It's a wild idea. As a motor spins faster and faster, it doesn't just use electricity. It actually starts to act like a tiny generator, creating its own voltage that pushes back against the power source. Now, here's where the transformer part comes in. The motor's main run winding creates the magnetic field that gets everything spinning. But as the rotor spins, it induces a new voltage back onto the windings. And here's the genius part. The start winding is built differently.
it has way more turns of wire, which means it acts just like the secondary coil in a step-up transformer.
And this is the aha moment. Check this out. Because the motor is basically acting like a step-up transformer, the voltage it generates in that start winding goes through the roof. You might only be feeding the motor 120 volts, but once it gets up to speed, that back EMF can spike the voltage in the start winding all the way up to 180 volts, maybe even more.
And that massive voltage spike, they call it the pickup voltage, is exactly the signal the relay has been waiting for. When the relay's coil senses that spike, it becomes a powerful little electromagnet. It generates enough force to physically pull on the plunger, which yanks the contacts apart, opening the switch and cutting power to the start circuit. Think about that. The motor literally generates the power to operate the very switch that protects it. It's a perfect, self-regulating loop.
So there you have it. Two totally different approaches, two completely unique but equally brilliant solutions to the exact same problem. How do you give a motor a hard kick to get it started and then get out of the way before it burns up? Let's just put them head to head. You've got the PTC starter, which is just beautiful in its simplicity. It's pure material science, a special ceramic that changes its properties with heat. And then you have the potential relay, a more complex mechanical device that uses the fundamental laws of electromagnetism to turn the motor into its own off switch. So why does any of this matter? Well, because it's a perfect example of the invisible engineering that makes our world go round. Tucked away inside the most ordinary appliances we use every day are these amazing solutions to really complex physics problems. Solutions that are elegant, reliable, and just silently doing their job for us day in and day out. And that really just leaves us with one final thought. The next time you hear that familiar hum from your AC or your fridge, you'll know the secret story behind that sound. And it kind of makes you wonder, doesn't it? What other hidden transformers and smart materials are quietly working all around you right now, just waiting to be discovered? Thanks for watching.